Test. Test, test. Let me know if you can hear me for people online. Okay, good morning. Let's get started. Let's continue on the Laplace transform. Okay. So you have the handouts from previous lecture. You can use that. It will come in handy. So in previous lecture, what we have done essentially to demonstrate what Laplace transform is. As you can see, this is a formula for Laplace transform. And then we also demonstrated on page 2 of the handout, what are the Laplace transform of some of the typical functions. Typical function basically means functions that you use often as input to the system. For example, unit step input, impulse signal, or ramp signal, okay, or sinusoidal signal. So then the corresponding Laplace transform is on this right side of the column there. I also mentioned that in this class, we deal with so-called causal signal. So we're basically looking at this column here. We consider they're causal. That's what you notice the first line in table here, consider all function defined as causal. So technically, if you don't see this, then you could just consider every function multiplied by a unit step function u of t. Right? So any function multiplied by a unit step function u of t, right? Then together they give you a causal signal. So you could consider there's a hidden multiplication of u of t behind each one of the function there, right? Behind each one of the function, right? So let's continue on the property, continue on the Laplace transform, that table over there. And we'll look at the mainly properties of Laplace transform, and then we'll look at some applications of Laplace transform. Properties basically means, something that you could actually make use of later, for your calculation of Laplace transform certain function. So first property is linearity. We talked about this already, so I'll just write it down. So linearity basically means the Laplace transform this operator L. So this is operator, you're operating on a function f of t. So this operator L is a linear operator. If it is a linear operator, then the superposition rule should be satisfied. And if you operate this operator on a function c1 f1 plus c2 f2, then it's equivalent to c1 L f1 plus c2 L f2. So this is what linear operator means, right? We have seen this quite a lot. Derivative is a linear operator, right? Integral is also a linear operator. A second property is called S-shift. We showed this actually in the previous lecture. So what this S-shift basically means, if you require to calculate Laplace transform of this function, so which is e to the power negative at times f of t. So then the S shift essentially says this equal to capital F of S. Okay? And of course, F of S is the Laplace transform of the function F of t. So this is called S shift. Sometimes we also call it frequency shift. Because usually we call the S is a complex number, sigma plus j omega. If sigma is 0, then you're left with j omega. That omega is actually considered as the frequency. So S plus A is like you have a shift of frequency. So what you need to basically be clear a relationship right here is, what is capital F of S? This is from the Laplace transform of the function f of t. And then if you multiply f of t with an exponential function, then technically you just have to shift this f of s by a constant a, okay, to the left side, of course, okay, plus a. That's called S shift. So I think in this table you actually have an example. For example, you can see this one here, right? So t to the power of n, its Laplace transform is n factorial over s to the power of n plus 1. Then if you multiply t to the power of n with e to the power negative at, all you need to do is replace the s with s plus a. Right? That's basically the property that we have just demonstrated. And this one, same thing. If you have the cosine omega t plus theta's Laplace transform, which is shown here, then the next time, if you're required to calculate e to the power negative at times cosine omega t, so go find the s. Right? There are two s here, one here, then shift. Sorry, this is a cosine omega t, right over here. Find the s here, and then replace s with s plus a and s plus a. Right, according to this S shift property. Okay, so then you get its corresponding Laplace transform. That's called S shift. And the next one is also very useful. It's called T shift or time shift. The time shift basically means you have a function f of t, and now you shift this function to the right by amount of a. Now, we assume every function is a causal signal, but just to make it mathematically more rigorous, so you could just multiply by this. Essentially, here is your original function, f of t times u of t. So any function times a unit step function, and you end up with just a causal signal, right? Because unit step function cut off everything that when t is less than 0. So if you shift this whole function, so let's suppose this is your function f of t, right, times u of t, then it's a shifted version to the left, to the right by a. It's basically, right, it looks like this. So that's what f of t minus a times u of t is, okay, times u of t minus a. And for this property, okay, so I'm not going to provide a proof anymore. For this property, so it gives you e to the power negative as multiplied by capital F of s. Capital F of s, again, is the Laplace transform of this original function f of t times u of t. I mean, if you know f of t is a unit step function, then you don't need to keep the u of t at here. Okay. So this is your function f, right? I think we have this property listed in the table over here. So that property is right here. Okay. And that's what S shifting is, T time shifting is. called a time shifting. And this next one is particularly useful. This one, when we use it to solve differential equation, it's called the time derivative or differentiation. So here's what this basically what it's about. You have a derivative of the function with respect to t, and you're looking for its Laplace transform. So take a derivative of this f, and then what's Laplace transform the result. So I'm going to provide a very short brief for this one, okay, and then the rest of you can just simply remember this. It is listed under the table over there, okay. But I think for this one we should probably just quickly look at the proof. Okay, the proof, okay, is strictly come from the definition of Laplace transform. So we're looking for the Laplace transform of whatever inside the operator bracket. So according to the Laplace transform formula, it's anything inside the bracket is a function you're taking derivative about, and then e to the power negative st dt. So this portion here is whatever inside the bracket that you're taking Laplace transform. And the rest of this is strictly the definition of a Laplace transform formula. So now you can clearly see you can cancel the dt. Then you're left with e to the power negative st d f of t. Okay. And then from here, this is the, what's the property again? You have a, someone help me out. What's the property for this? You know, when you have a e and d of this, you end up with what? E to the power negative st times f of t, plug in the limit, and then switch the order. What's the name of the property? Does it ring a bell? When you look, does it look familiar to you? Integration by part, exactly. Thank you very much. Yes, excellent. Yeah, I really find when you're getting orders, sometimes just on the tip of your mouse and you just kind of spit it out. Yeah. Integration by part, right? It's one of the integration technique. So, and then you can plug in the limits, okay, plug in the limits into the first term. And when you plug in the infinites into t, okay, I remember we always consider there's a region of convergency. So we would consider there's a region convergency. So then that term, when you plug in infinite into here, will be 0. So basically 0 minus the second term. When you plug a zero into the t, which is 1, so this is f of 0, right? Left with f of 0. That's what you have for the first term. And the second term here, okay, you can take the derivative of this exponential term. Okay. Derivative of this exponential is back to t. This term here is negative s d negative s e negative st dt. Right, so that's the d e to the power negative st equal to this, okay, with respect to t. So you're taking derivative, you're taking integrals with respect to t, so you can take the negative s out of here. And negative will become positive. But what's left inside f of t e to the power negative st dt. Okay. Okay, so now you sort things out. So negative become positive, and then this whole term, the integral term here. That integral term, you look at it carefully. This is basically Laplace transform for f of t, right? Which is f of s. So then you end up with the derivatives f of t in Laplace transform It basically is capital F of S minus, there's S over here, minus F of 0. Right, so that's the property. If you're looking for the derivatives Laplace transform, you don't need to recalculate everything. Just look for the derivative, just look for the Laplace transform capital F of S, and then multiply by S minus F of 0. F of 0 means it's the initial value for the function F at the t equals 0. Then you get its Laplace transform. So let's rewrite it here. Okay. That's that property called time differentiation. And in the next, probably next lecture, not today's lecture, we're going to use Laplace transform to solve second order differential equation. And the procedure, the first step procedure is to transform the time differential equation into a Laplace equation, S equation. So we're going to take Laplace transform of both sides, right? Then you will need this property. Now, similarly, you can also take Laplace transform for the second order derivative. And this, without a carry out a detailed proof, you can take a look at the lecture notes. I do have it. And it will give you S square F of S minus S F of 0 minus F prime of 0. So that's the property for second order derivatives Laplace transform. So you look at the right side, right? Everything is known. You will be able to get the capital F of S. You know, if you have the time function, you certainly can calculate its value at F of 0. You certainly can calculate its derivatives at a t equal to 0. So that way you get this. So F of 0, F prime of 0, and we call them initial conditions. And you will be able to have this, right, if you're required to solve this kind of question. Okay, so that's time differentiation. Now this is number 4 and number 5, integral. So integral, you're looking for is if you have an integration of a function. So you integrate f of tau from 0 to t, and you will end up with a function f of t. You end up with a certain function of t. Right. So then, what is its Laplace transform? Again, without a proof. Okay, I'm showing the proof right here. Its Laplace transform is capital F of S over S. Okay. Yeah. So these two properties, okay, number 4 and number 5, are particularly useful for us to solve differential equations. Now, but before you proceed, I want to bring it to your attention a little bit of observation. All right. So if you observe the results of the properties that we have written down at here, so this property, and this property. Okay. This is the first order derivative. And you have S times capital F of S. This is a second order derivative. You have S squared times capital F of S. This is a derivative. You have something divided by the S. So as you can clearly see, when you have a first order derivative, you have S. As the order go up, you have S squared. If you have a third order derivative, you probably should imagine you should have what? S cubed times F of S, right? And you have an integration here instead of a times S. Now this time you're divided by S. So the general rule of thumb, when you multiply S with something, with a function, okay, whatever function, S function typically, of course, So S, what it does is it's a derivative action. So one single S multiplied by a S function, it's a derivative action, a single derivative action. So then, of course, S squared, right, will be a second order derivative action. So that's how it goes up as order. Then 1 over S, okay, when you multiply 1 over S with, okay, something at here, so whatever the function there, the 1 over S, when you look at that, that means, okay, I must have a integration action. So this is a integration action. So you will learn more about signal systems and especially control system, right? So one of the control system action you must probably have heard is called PID, proportional, integral, and derivative. And the PID controller takes the form KP plus KD times S, and then KI 1 over S. So this actually represents, it's a PID controller. Okay. So what this controller is doing is, okay, you apply the controller into your system, and so there's some signal coming into this controller, right? So this is a box. So there's a signal coming into this box, and the box will spit out some other type of a signal. But if you look at this expression at here, what it does is KP is it's a number, it's a constant. So when you multiply the number with a signal, what it does is what? When you multiply number with a signal, what does it do? Let's say the signal is cosine 2t. Now you multiply 2 is 2 cosine 2t. So the output basically is being amplified. Okay, so that's what it does, right? And you multiply this KDS with the input signal. As I just said, S is a derivative action. So in time domain, the equivalent is you're like taking derivative of this input signal. Okay, and then if you multiply this with the input signal Ki with 1 over S, 1 over S is integral action. So you're literally just integrating the input signal, right, with this integral action at here. Now you might wonder, why do you do this? That's a different future subject, how this is actually helpful when you're controlling certain systems, certain actions of the system. Okay. But mathematically, right, this is essentially, if you had to remember something, what is S? What is 1 over S? The simplest meaning that you can remember is S times something give you a derivative action. 1 over S times something give you an integral action. Okay. So let's take a look at a couple of examples, how we can make use of the properties that we have just written down at here. So let's look at this example. Laplace transform of this function. So e to the power negative 4t times u of t minus 1. So when you apply, always remember how if you want to apply certain properties that from the table, okay, this is the properties over here, right? This is the result of the S function. You have to be able to write whatever you have it inside the bracket, okay, to be in the same format as in that table, okay, before you can apply. So for example, right, most probably I want to apply this property. So if you have a shifted F, and then its corresponding Laplace transform is given by this. If you recall that, it's called the T shift, right? Okay, so let me write down this property at here. if this is a property I need to apply, so let's go back to whatever inside the bracket. Let's see if you can make use of the property right away. All right, so let's compare term by term. I certainly have a u of t minus 1 at here. So you also have a u of t minus a. So these two terms certainly is the same format. You can actually see, oh, a gotta be what? 1, right? And then you look at this term here compared to this term. So this term says it's a function f, or originally it's a function f of t, and then you shift to f of t minus a. So you look at this function, what you have here, e to the power negative 4t. That is not in the format of what? If a is 1 here, right? If a is 1, then whatever before this u function technically should be negative 4t minus 1, right? Before you can actually apply this property. But the current function before the u is not e to the power negative 4t minus 1, it's just e to the power negative 4t, right? So you cannot make use of the property right away. So if you want to make use of this, you have to manipulate somehow. Then you can use it. Okay. Yeah. So that's what we're gonna do. So now, but we have a bigger direction now, right? That's where we want to go. So I'm gonna manipulate this term to match the format, okay, in the property. Now, as I said, to match that, basically you want that to be negative 4 times t minus 1, right? That's what you want. However, you cannot change it. So if you forcefully write this negative 4t into negative 4t minus 1, so what do you have to do? Sorry, come again? U of t minus 2, well, then I don't have a match over these two anymore, right? Now I want to keep this u of t minus 1 here so that I have, you see here, I have exactly t minus a, in my case, t minus 1, t minus 1. Okay, that's what I want to keep. Yes. Multiplied by e to the power 4. Exactly. Is it multiplied by e to the power 4? Actually, it's very close now. So let's, before multiply e to the power 4, let's just see. This is your negative 4t. I want to keep negative 4t. That's what I mean, right? But I changed to negative 4 times t minus 1. So if I want to keep as negative 4t, what do I need to do for this term? Negative 4. So I have to minus 4, right? So if I minus 4, then I'm not changing at all, basically. Let's clean up this a little bit. So I have to minus 4 because you look at this one here, negative 4 times into the bracket is positive 4. And that's the extra term we just added. So I had to get rid of the next term, which is to minus 4. Is that clear? Anyone's not clear to this step here? So the bottom line is we're not really making any changes, right? We're just basically add a 4 and then minus a 4 to this term. Okay, but by doing this, for the first term, this is like a e to the power of a plus b now. So a is this and b is this. So you got two terms addition, e to the power of a, which is e to the power a, e to the power b. So I can rewrite it as a e to the power negative 4 times t minus 1, e to the power negative 4, and ut minus 1. E to the power negative 4 is a constant. Laplace operator is a linear operator. So when you have a constant inside this bracket, you can always take the constant out of the bracket. So now you can see inside this bracket for Laplace transform, you have exactly the formats of the property that you can make use of. So this is the property here. The property has a u of t minus a, has a function of t minus a. So here you have a u of t minus 1, and this is a function of t minus 1. So now I'm ready to apply the property. And the property says e to the power negative as, a is 1, so negative s. Capital F of s is Laplace transform. So what's capital F of s? Is Laplace transform f of t. So you look at this function. This is your function f of t minus 1. And if you replace the t minus 1 with t, then you get back the f of t. So that's Laplace transform e to the power of negative 4t. And this is a property I want you actually try to remember. Laplace transform of an exponential time function, right, should be s plus 4. And that's clearly given in the table, which is this one here. And there's something actually, once you do more, I think you will be able to memorize this quite easily. So overall, the results, right, you multiply here, you multiply by 1 over s plus 4 added here. And that's your f of s. And sort things out a little bit, so you will get e to the power negative s plus 4, and then 1 over s plus 4. Okay. Just a little bit of deeper extension from here, or understanding this, right? So as you can clearly see, in the future, right, if you see an exponential e to the power of, for example, let's call it just whatever number. If you ever see e to the power negative as multiplied by certain Laplace s function, so whatever function, maybe this is s 1 over s squared plus 2s plus 4, for example. Okay, yeah. Whenever you see an expression like this, then what's jumped to your head actually, right? Because ultimately you can transform this back into a time function. When you convert it to the time function, whatever the time function that end up with, it should be, there's some sort of a delay, okay, in your time function. So that's what this exponential term does, right? So time function must have a delay. This is also very useful when you design a control system. Many real-time systems have delay. And when you transform the time function of this actual system into a Laplace format, into S function format, if the system has delay, then your S function will have exponential to the power of negative something S, okay, in your expression. So that's a direct, basically, knowledge which, okay, the system has a delay, for example, right? We look at the S function. Okay. So I would consider this is relatively a tricky type of application of a Laplace property, right? You just have to do one manipulation first before you can actually apply the Laplace property. Two more property. One is called initial value problem, initial value theorem, and another one is called final value theorem. All right. So let's say I have a time function f of t given. Initial value, let's call this is IV. Final value, let's call this FV. Then often in time, you'll be interested to know, so essentially, what is the function's value at t equal to 0? And what is the function's value at t equal to infinite? All right, so this is called initial value. This is called final value. So let's say you have a certain system, mass spring damper system, and then you apply a force or initial condition. So you would be interested to know, so how does it behave at the beginning, and how does it behave as t goes to infinite? Right, that's called a final value. So some system will settle down, and some system will probably still oscillating. So there is no set value, and some system will actually probably go crazy, right? Go infinite large. We call that unstable. So that's the idea why you wanted to know the final value, or sometimes also infinite initial value. So of course now you can clearly see. So okay, so if I have the time function, then let's just plug in t equal to 0, then you get initial value. You plug in t equal to infinite, then you get the infinite value, right? Final value. So that's definitely one way to think about it, right? So for example, let's say you have this function, and I can plug in t equal to 0 into the function. I get 1, so that's my initial value, and I can plug in t infinite into the same function. So what do you think if I plug in t as infinite into the function? What should we get? Zero, right? So e to the power negative 2t, this is an exponential decay function. So you plug in infinite to here, you will be 0, approach to 0. Of course, cosine 10 times infinite, whatever the infinite is still oscillates. It's hard to say, right? Yeah, but it's a bounded value. Okay, so bounded value times infinite small value, so you end up with a 0. Okay? So that's how you get it. Now, alternatively, right? This is basically the property we're going to show here. Alternatively, we can also get this initial value and the final value, okay, after we convert the function f of t into a s function using a Laplace transform. So let's do that. I'll show you the property. Here's your f of t at here. If I do a Laplace transform of this function, so use the property at here. So cosine omega t times an exponential function, then its Laplace transform is s plus a over s plus a squared plus omega squared. So in this case, a is 2, so s plus 2, s plus 2 squared, omega is 10, so 100. This is the f of s for the f of t. And now, if I'm going to get this initial value f of 0, so this first property is you can use this limit s go to infinite s times f of s. You can get exactly the same f of 0 by operating on s times f of s, but the s has to go to infinite. So let's try this together. S times f of s, here's f of s, so you time s, and what do you get? So you get s times s plus 2 over s plus 2 squared plus 100. And then the limit is s to infinite. Okay. And taking the limit, this is kind of back to your first year. You know, there are different ways for calculating the limit. But in this kind of question, you look at the numerator and the denominator. Both of them are polynomial. And the numerator has order of 2. Denominator also has order of 2. So the way to do this, because s go to infinite, you might want to divide s squared, okay, for both the numerator and the denominator. Then you end up with limit s to infinite. When you divide s squared for the numerator, right, you got s squared plus 2 over s. So basically, you're gonna 1 plus 2 over s. And the bottom here, you end up with 1 plus 4 over s plus 104 over s squared. After you expand this s plus 2 squared term. And s go to infinite. So any terms that has s as a numerator will go to 0. So you end up with just 1, right? Which is the same result as you manipulate in the time domain. So this property is what I mean by initial value property or theorem. To get the initial value based on the Laplace S function. Similarly, you have a property for final value theorem. So this time you are letting s actually go to 0. And you're still looking at the expression s times f of s, but s go to 0. Okay. And this one is actually pretty straightforward. If you go, you can just simply replace the s with 0 for both the numerator and denominator. And numerator, denominator, you replace s with 0, you end up with 100. At denominator, you replace s with 0, you end up with 0. So you just get a 0, right? Yeah. So this is the property. These two here are so-called initial value and the final value theorem. These two properties, you might think they're redundant. You can think, why do we want to do? Because if I have a function f of t, then why don't we just get it used in time domain, right? You will see that's why it's useful later, because if I have a system, okay, not just a simple signal. Right? If I've got a system described by a second-order differential equation, right? Before we actually are able to obtain the solution for the system output, often in time, it's much easier to obtain a Laplace transform S function for the system output. So that's where you can do an initial check. Okay, so I got S function for the output. So let's take a look at the initial value and the final value. Is the system actually going to be a stable system, or is it going to be an unstable system? So that's particularly useful for this final value theorem. Okay. So we'll see that next. Any questions on this property? Good? Yeah. So there are quite a few properties were listed here, especially in the first page. Now, often in time, as you can see, some of the useful ones, okay, in terms of our future usage. These two, and this one here, okay, and this one we're going to cover next, are particularly useful in this class. Okay. Any questions before we proceed? I don't have much time, but I can actually just write down. I'll write on one property, one application. So I do have a couple applications that we can show how to use Laplace transform. And the number one application is the relationship between Laplace and convolution. So we're getting back this convolution again. So if you recall, convolution basically is if you have a two function f of t and the g of t, and let's assume that f of t's Laplace is f of s. G of t's Laplace is g of s, capital G of s. Okay. Then if you're going to calculate the convolution between f of t and the g of t, right? Now you have an alternative solution, alternative method is that you can apply the Laplace transform to this convolution, which turned out to be the multiplication of the two s function, capital F of s and the g of s. This is the first application of Laplace. If you apply the Laplace operation to the convolution, then you no longer need to do this convolution, which is integrals, remember, right? Then you can actually simply multiply the two s function together. And that's actually one of the points I pointed out to change perspective. Remember, you can multiply a and b. You can do multiplication. But if you use a line, then you no longer need to do multiplication. You just have to do a addition, right? So what this property or theorem is telling us is you can certainly calculate convolution in the time domain by using the graphical approach, integrations, no problem at all. However, I could also do is take a Laplace of it and then calculate the multiplication of two functions. After we get the multiplication of the result of two functions, of course, we're going to have to convert it back, okay, to the time function. So basically, you have one more step to go, but you no longer need to use any integral action anymore, operation anymore, like what's originally involved here, right? So that's called a change of perspective, right? So that's what we're going to demonstrate next in the next class. How we can apply this and how you can actually see some of the questions will become much easier to do, okay, in this direction this week, rather than calculate out using the typical integral action. Okay. All right, so let's do that in the next lecture. So I'll stop here today. Okay. Any questions? Feel free to come over. Yeah, you can apply. Bye.